Okay, so great. We talked a little bit about the online setting, and now I want to go back. I want to say what we said was not explicitly about fairness, right? That's okay. I mean, we can talk about things that aren't fairness, but talking about, calibration and these tests. So why are we talking about it in the summer school about fairness? And the reason is that we're trying to make sense about, this question of predicting probabilities. So we want to know what the tools are in our arsenal for coming up with meaningful probabilities. And meaningful probabilities are kind of a fairness issue in their own right. Right? Like if someone is going to try to predict my probability of having a heart attack and putting me on some medications or interventions based on that probability, I want that probability to be meaningful, and it can be a fairness issue when we're talking about, are probabilities meaningful for, minority or protected populations. And, even if just computing if you tell me, well, the data are biased, reality is biased, I don't care about these probabilities, they're poisonous, well, I still think that we want to be able to understand what are the probabilities in the data as we see it so that we can meaningfully apply interventions or corrections or affirmative action. So tying it back to fairness, and I want to do that more so in the batch, focusing on the batch setting for the rest of our time today. So just quickly, we have again our familiar friend, the distribution D. We have our learning algorithm that gets samples xi, yi, drawn iid from D. So there is some underlying distribution, and we output a predictor, a risk predictor, or scoring rule, p tilde, mapping individuals to scores between 0 and 1. And in the back of our heads, we have this unobtainable P star, which is defined as the correct probability. Okay, so P star of X is the correct probability of the outcome being 1. Now, a point I didn't talk about when you asked about soundness in the previous lecture. So I want to say the defining problem or a defining problem is that we don't know. Is P star deterministic? Right? Is it really the case that everyone, either everyone in the data set, will return the loan or will not return the loan, and that's a deterministic bit? Is there really entropy? Is there really randomness going on? And if we wanted to have soundness before, kind of like a soundness requirement, that would require resolving this question. Are there probabilities or not? In particular, if your soundness requirement would say that assuming everything is deterministic, I don't want to accept probabilities with lots of junk entropy in them, then in order to achieve soundness, you have to resolve the question of whether there is probability or everything is really deterministic, everyone's fate has been set. So it's a deep question, and it'll be hard to get that kind of soundness guarantee. So thanks, Cynthia, for pointing that out. Good. So we want to output the P tilde, really the unobtainable ideal, that we have in our heads that we can define but never really see is P star. And the question is, what does it mean for P tilde to be meaningful? And, we talked about loss minimization in the context of classification, and we can also talk about it in the context of prediction or risk scoring. So we can define a loss function like the squared loss or the logistic loss or whatever, the L1 loss, whatever loss function is your favorite, we can define it. We can try to minimize the loss of our predictor. We can compare it, as we do in the agnostic learning setting. We can compare the loss experienced by our predictor P tilde to some benchmark class and try to beat the benchmark class. But still, at the end of the day, the question is, what is a good loss? Is our loss good? Is it not good? Again, has to do, we never know, because we don't know what, if P star is deterministic, then maybe we can achieve loss 0. If there is probability, then maybe loss 0.2 is really good. And when we're talking about complex tasks, we're going to have a loss, right? We're not going to be able to deterministically predict whether every defendant is going to recidivate or not, whether every individual is going to have a heart attack or not. The correct answer is out of reach. So, nonetheless, loss minimization is a very popular framework when you're doing risk scoring or risk prediction, and I want to revisit it from a fairness perspective today. Okay? So, when we are thinking about fairness, is this orange terrible or is it, yeah, it's terrible, okay. I really like having colors, but maybe we're just going to be monochromatic for today. Okay. So fairness, when we're talking about the batch supervised learning setting, so batch means we have our underlying distribution, supervised learning means that we have these labels, labeled examples, and now we want to talk about, oh gosh, I give up. So, when we talk about fairness, there are lots of concerns we could think about. Yesterday, when we talked about fairness, we were talking about classification, but you could similarly think about risk scoring. We assumed we had the metric, and the metric was truth for fairness. So we didn't really need to worry about, well, we worried about fairness, but we sort of had this vehicle conveying all of the fairness concerns, and we don't have that today. So let's spell out some of these fairness concerns that we've been talking about. So we could have biased features. We could have biased labels. We could have bias in representation in the data. And any of these, if we have them, of course, if we're trying to do loss minimization, we're going to learn, if we're trying to learn something that is reflective of the data, we're going to have problems come up, right? Especially if the labels are biased. We're going to learn something that perpetuates that bias. But I want to talk today about, so nonetheless, I do want to talk about fairness when we are just trying to learn what is going on in the data. Okay? So we have our data, we're trying to accurately convey these probabilities or meaningfully convey these probabilities P tilde of the labels for the data at hand, and I claim that there are still fairness concerns. Okay, so there are also fairness concerns in learning in the learning process itself. So even if we're just trying to sort of meaningfully convey what's going on in the data, there are fairness concerns, and in particular, the minute we say that there are subgroups in the data and we want to protect them, and we know that the predictor that we output is going to make mistakes, it's not going to be perfect, it's not going to be P star, we have this question of whose predictions are meaningful, right? Like whose probabilities are being meaningfully conveyed or learned by the predictor P tilde. And this is a concern because if we have a minority, so machine learning often tries to, especially when doing risk minimization, simple predictors are valuable because they generalize well. So we often regularize our learning and we try to make the predictor simple. And so it's very reasonable to worry that if there is a subpopulation, even though the predictor is trying to minimize loss, it's also trying to be simple, so it generalizes well. And maybe it misses what's going on in some subpopulation that is different from the general population. And this is not a theoretical concern if we're thinking, for example, about medicine. And we'll have a talk by Noah Dagan on Thursday, who will tell us about bias in medical risk predictors. And also, I think Zayad Obermeyer will also touch on that. I'm sure he will also touch on that. So, where are the errors happening and whose predictions are meaningful is also a fairness concern. And that's what I want to focus on today. I don't want you to stop worrying about the biased features and the biased labels and the biased representation in the data. I think those are all really important questions to resolve, and maybe we'll say something about them. I think that even for those, as a first step, having a learning process that meaningfully conveys what's happening in the data, also for protected groups, is an important first step. Yeah. Oh, I just meant the issue that some populations are underrepresented in the data. Okay, so for example, the facial recognition example Cynthia spoke of, she mentioned that, I don't know if that's the problem with the facial recognition issue, but that's one explanation that people have brought up, that minorities are less represented in the corpus of training data, but other concerns, like we talked about the lenses and the cameras. And, so this is not meant to be an exhaustive list, just like some things to worry about. And today I want to talk about meaningfully conveying what's happening in the data and who do the errors hurt. Okay. So starting off with group fairness, one thing we could hope to do is identify a protected group S and start making some meaningfulness requirements about the predictions for S. Okay, so it makes a lot of sense to require meaningful predictions on S. So let's try. And going back to what we talked about in the online setting, we can make similar sort of sanity checks or meaningfulness requirements about the probabilities. And the example I want us to have in mind, which I think will help, is applicants for loans. Okay, so we are trying to identify qualified applicants in the loan pool. And the concern is that, we have a protected group, and for some reason or other, our predictor P tilde is not identifying the qualified loan applicants, the ones that have a high probability of returning the loan. So one thing we could require is, this is going back or inspired by the criteria we had for online learning, is we could require that the expectation of the probabilities being given to the members of S is accurate. Okay, so this is alpha accurate expectation. Okay, so basically the score, if I look at the expectation of the labels conditioned on membership in S, I want this to be close, I want the predictions to be close to that. Okay. So, I want the difference to be at most something like alpha. Okay, so if on average the probability that an applicant in S returns the loan is 90%, then the average of the predicted probabilities should also be 90%. A very minimal requirement of meaningfulness for the probabilities assigned to the members of S. And we could also talk about alpha calibration or calibration up to some error alpha on the members of S. I'll define it formally tomorrow. We saw an approximate definition for the online case. So, as always is the case for group fairness definitions, if we don't have this, then I think we have a problem. Right? If on average 90% of the applicants from S are returning the loans, but the average probability predicted is much less than 0.9, something is fishy, something is going on, and we need to sort of re-examine our predictor and what's happening. So, this is a meaningful red flag, but it's very weak, right? If all we're guaranteeing is this kind of group fairness notion that on average over the entire set S, our expectation is okay, that's very weak. So for example, it could be that half of the applicants in S are very unqualified. They have probability 0 of returning the loan, and half of them have probability 1 of returning the loan. And we assign everyone a probability of a half, and no one gets the loan because that's sort of below the threshold where it makes sense for the bank to grant the loan. So just the fact that the expectations are accurate doesn't say much because we can smush everyone together Right? The predictor can be smushing everyone together. It's not making meaningful distinctions between qualified and unqualified. That's also true for calibration. So smushing everyone together, and I think Cynthia gave that example. There was some discussion of it. Smushing everyone together will still give calibrated probabilities, but is not meaningfully distinguishing between qualified and unqualified. Even worse, the predictor could be marking the qualified as unqualified and the unqualified as qualified, kind of flipping the correct answer, and still the expectation would be accurate. So it's a weak property on its own. Yes?
I was just wondering, can you trivially fix this by requiring the same for all subsets of S2?
By requiring?
By requiring the same host for all subsets of S.
The same?
The same, like, alpha.
Good, so keep that question. So for all subsets of S is going in the right, it's definitely going in the right direction. Really what I would want is for the expectation to be accurate on the qualified, right? I want for the qualified applicants, for the predictor to be showing that they're qualified. So you're saying, well, maybe we could just require that not just on S in aggregate, but on every possible subset of S, the predictor is accurate. That would be great if we could do it, but it's too strong. Because in particular, the predictor is making errors, so sort of a posteriori, I can look at the members of S where the predictor is erring in one direction, and, say, underestimating them. And for those, the expectation is not going to be close. So unless I can really approximate the true probabilities, and those are out of reach, that's often too hard, I can't guarantee for all subsets of S. What I will try to do is to guarantee for a very, very rich collection of subsets of S. A collection that's fixed in advance as opposed to a posteriori. And that's going to be the direction that we go in. Great question. Yeah? Yeah, it does, and I will so there's various ways of handling that. The way I will handle it today is by putting a kind of a lower bound on the size of the S's that we care about. So I won't care about sets that are very, very tiny, that have very, very tiny weight, according to the distribution. So there will always be some lower bound tau on the weight of sets that I care about, and for sets that are that large, I will require that the expectation is alpha accurate. But I should say, I think the point you're trying to make is that if the set is really, really tiny, then maybe I won't be able to obtain error alpha, and maybe that's also not meaningful because the set is so small, like who cares?
Well, I was actually saying we might care, right? Like, to your bias representation point, that means the least represented, we also give them no guarantees, right? Like, this won't work for the...
Yeah, so it's a problem, right? Like, you're right that, maybe I'm making my life too easy by ignoring the really small sets, and maybe they are important and they're not in my data, and I agree that it's a serious problem. I think that to some extent, depending on how we define the problem and what our scope is, it just might be an impossible problem for us to tackle once we are saying, okay, but we're bounded to this distribution. Okay, I can't tell whether the set is tiny because they just don't exist in the world or because they're underrepresented. So it's a very, very important problem, but sort of at a different scope or a different place in the pipeline to worry about it. Almost, but not quite, because I do want to say that, okay, maybe if they're very, very, very tiny, then I have to give up. Or maybe trying to require this kind of guarantee, well, maybe there should be 15% of the population. And in my training set, they're only 5%. And so the learning algorithm sort of ignores them because that's not where it's going to be getting, its loss minimized. But maybe enforcing this type of property or a different property on sets that are, say above 3% of the distribution will force the learning algorithm to pay attention to it because there is data there. They are 5% of the data. So, there is some potential mitigation measure here. Okay, good. So, as a starting point, this we said is certainly if we don't have an alpha accurate expectation, that's bad. On its own, not very strong. So now the idea is, well, maybe we wanted to require it on every subset of S. And I want to make the point, and this is the point where intersectionality comes in, maybe I don't just care about S, there are many protected groups that I care about, and for all of them I want alpha accurate expectations, not just for every protected group, but for the qualified loan applicants within each protected group. And I don't know exactly who they are, so I'm just going to try to look at a very rich collection of intersecting sets and simultaneously guarantee accurate expectations for all of them, or calibration for all of them, or some other accuracy or fairness requirement for all of them. And that's sort of the multi-group or multi-X framework that I want to talk about today for the lecture.
Okay, so are you assuming that your rich collection of sets then is somehow a superset of the sets that you actually care about?
I'm assuming that it is richer than just like the list of sets that I care about, because I do want to capture also the qualified loan applicants within the sets. So somehow what I would really like to do is to guarantee, and I'm going to stick with the running example of multi-accuracy, but I'll talk about other things that we may want to guarantee. So I want accurate expectations, I'll just call that AE, on every kind of identifiable set. And I will also say we need them to be large enough in terms of their mass according to distribution. Pure question. Okay, so ideally what I would want is that every set that we can really identify given the features we have and with some reasonable complexity, within some reasonable complexity bounds, for all of them simultaneously, we want to guarantee alpha accurate expectations. If we can identify a set where the expectation isn't accurate within some bounded class, then things are off and we need to fix our predictions. So, yeah, an identifiable, I want to emphasize there are two things that are going on here. First, given the features we have. So again, that's a big problem. And it's the features are a serious issue, and maybe the features we have are not rich enough, in particular not rich enough for protected groups, but nonetheless, the definition is going to work with the distribution that we have in our hands and those features. So every set that we can identify from these features and within some computational bounds. Okay, so, and this is what we call multi-accuracy. And analogously, we could define, and we will define, multi-calibration. So, it's parametrized. The definition is parametrized by a collection of sets C, a collection of subsets of the universe, and by parameters alpha, that's our alpha that we're going to require for the expectations, and we'll also have some tau, which is the minimal size or probability, the minimum size of sets that we actually care about according to the distribution. The question?
Yeah, how do we, is this the set, all the sets we care about given as input to the problem? And how do we deal with, isn't this like a fairness issue by itself, like choosing the sets we care about?
Totally. So we'll talk a lot about it, and Cynthia will talk about it tomorrow when she talks about scaffolding sets. But who the sets are is a serious issue. And our fairness guarantee is only going to be as strong as the appropriateness of the collection of sets that we're dealing with. Nonetheless, I think it's a big step forward from kind of the group fairness where we're just looking at a protected set or a couple of disjoint protected sets in aggregate. And the nice thing about it is that if we have a collection of sets and we end up not being happy with their expressiveness and the strength of the fairness guarantee, we can enrich the collection of sets, right? That's something we can play with. It's a knob we can turn. Okay, so predictor P is going to be C alpha tau multi-accurate if P is has alpha accurate expectations, alpha accuracy of expectation, for every set S in the collection C, that has high enough weight according to the distribution. So the probability according to D of S, so the probability when we pick a random X according to the distribution D that it lands in S is at least tau. Okay, so simultaneously for all of these sets, I want the expectations to be alpha accurate. Okay, and you could think about this collection, so, you know, from a complexity theoretic perspective, I would want this collection to be all of the sets that are identifiable in polynomial time or by a polynomial size circuit. That would be a really strong definition, right? For every set that we can identify within feasible computational bounds, the accuracy looks okay. So maybe the accuracy on qualified loan applicants isn't okay, but that's because no one can identify who they are. If we can identify who they are, there will be some meaningfulness to the predictions.
I don't know what it means to that it's identifiable with polynomial complexity, but I wonder if it's the same as what I was going to say. If you, instead of a collection of sets, you take a collection of observables, which are polynomial, and then you condition on the values of these observables being approximately correct, then the difference between the expectation of whatever thing you're measuring conditioned on that from the true expectation is less than alpha. Is that the same thing?
I don't know. So what do you mean when you say take polynomials?
Well, I mean, take observables. You construct certain expressions on your data, or I imagine polynomial in some sense, and you constrain the value of those expressions. So rather than the expressions being characteristic function of a subset, you just take more complicated things which are constructed out of such things. Is that it?
Maybe. I mean, it's some, so I think what it is you're describing some computational model, and you're saying that for everything that computational model can capture, you want the expectations to be accurate. And now we're talking about what the computational model is. You're talking about maybe bounded degree polynomials, the features. I'm talking about Boolean circuit complexity and like the size of a Boolean circuit constructed on top of them. We could talk about decision trees. We could talk about hyperplanes. We could talk about whatever your favorite computational class or machine learning class is for trying to identify subsets. We could work with that. Or that could be plugged into the definition. Okay. So we have a lot of flexibility there. And in particular, I encourage you to think of this collection as exponential. Okay, so we really have a huge collection of sets, and we're simultaneously worrying or giving guarantees for all of them. Of course, this is going to raise issues of running time of the learning algorithm, and we'll talk about that extensively, so don't worry about it. Or worry about it, but know that your worry will be shared and discussed, and good. Now, I want to say that one nice thing, or not so nice, okay, go ahead with the question. Yeah.
Sorry. Is it strictly weaker instead of talking about the complexity of the richness of sets, if we instead bound the complexity of P star? Like we don't know what P star is, but we say this is the best, like the idea would be like for linear regression we get something like it's a blue estimator, best linear.
Yeah, so the question was whether instead of talking about the complexity of the sets, we could talk about the complexity of P star. It's a good question. So I don't want to assume something about the complexity of P star. I don't know what P star is. It's some complicated process out there in nature. And I don't want to assume that the complexity of nature is bounded. If I did, then I could come up, by exhaustively searching over all the possible natures within a bounded class, I could come up with a perfect answer onto P star. So I don't want to do that. What I do want to say is that if P star is bounded in the way that you want it to be, then if we insist on accuracy for everything that is captured by that complexity class, we will actually end up with a good approximation to P star, and it's related to what Cynthia will talk about, just things that Cynthia will talk about tomorrow, perhaps. Good, so I want to say one good thing or bad thing, depending on your perspective here, is that there is no tension between multi-accuracy, which has to do with the accuracy of expectations, but as the name hints, there's no tension between that and between loss minimization or having accurate predictions or the predictions getting as close as possible to P star. P star itself will be multi-accurate, right? It has, for every large set, the expectation of P star is very close to what we see in reality. So there's no tension here. And in fact, the more we enrich the collection of sets, the more potentially accurate we will have to be in order to achieve multi-accuracy. Okay, so kind of enriching the collection of sets will not hurt accuracy in terms of loss minimization. As opposed to if we wanted to do something different, like kind of try to, we could do other multi-things, like multi-calibration. Calibration is also an accuracy property, so that's not in tension with accuracy. But if we started wanting to think about things like multi-parity, okay, so talk about enforcing statistical parity between, a very large collection of sets, now we have to really think carefully, because if we start enforcing parity between qualified and unqualified loan applicants, we can't get any accuracy. So if you're trying to get variations of this multi-group fairness for other fairness requirements, you sort of need to pay attention carefully to what you're doing and whether it makes sense or not. Two things I guess we've said, but I want to point out or highlight. So first, the sets here are playing two roles that are sort of coming up in the discussion. One role is they're capturing our demographic subpopulations that we care about, protected groups for which we want to have guarantees and we want to identify the qualified loan applicants. But the other one is that really the sets are not just trying to identify the demographic group, but exactly identify the qualified loans, separate the qualified loan applicants from the unqualified loan applicants. And if we can do that to some extent within this collection of sets, then multi-accuracy becomes quite meaningful. Good, and as I said, there's no tension with accuracy, and of course, if the data are biased, then just enforcing multi-accuracy will, in a sense, enforce perpetuating the bias in the data. And that's a really serious concern, and I encourage you to think about it. The one thing I do want to say is that it can be a good starting point. I said it before, I'm emphasizing it again now. It can be a good starting point. Having a multi-accurate predictor, maybe now you're actually seeing what's going on in the data, and it can be a good starting point for applying affirmative action. Okay, as opposed to doing some learning where the behavior on your protected groups is not even being captured in the predictor, and so there's nothing to talk about in terms of affirmative action. Okay. Good, other questions? So, one thing you might object immediately and say is that, I'm talking here about enforcing accurate expectations for an exponential collection of sets simultaneously. Is this even achievable? Right? Like, maybe if I want accuracy on one set, I have to give up on another set. We said that P star itself will be multi-accurate, but can we get multi-accurate predictors without coming close to P star? Okay, or is this just too strong a notion? Okay. Can we learn a multi-accurate predictor, and what's the complexity of learning? So, good. So let's answer all these questions. So the answer is that yes, we can always learn a multi-accurate predictor. We can do it using few samples. And the predictor itself is not going to be much more complicated than the sets themselves. Okay, so say we're trying to do multi-accuracy for Boolean circuits of size S, the predictor will not be, looking at the predictor as a Boolean circuit, it will not be much larger than S. So that's some good news. And then what we'll talk about is the running time in order to do learning, which is large. And I think that's what I wanted to say. Good, so the theorem I want to show, the learning algorithm that I want us to see today, is that we can always learn a multi-accurate predictor. So for every collection C, I'm thinking of it as finite, although you can get versions of this theorem. For infinite collections, the running time issues become more confusing, so I'll think about the collection as finite. for today. And for parameters alpha and tau that we want, we can obtain, there is a learning algorithm that will learn. So first off, there exists a predictor P that is C alpha tau multi-accurate. Let's call that MA for now. It can be learned, or one such, there are many such predictors. It's not just one, but there are at least one. And such a predictor can be learned from relatively few samples. So the number of samples is just polynomial in 1 over alpha, 1 over tau, and logarithmic in the size of C. And for infinite C's, you could think about replacing this with VC dimension or stuff like that, but I won't do it today. The size of the predictor complexity is roughly, so I don't want to be, I don't want to define too accurate, I don't want to pin down exactly the notion of complexity that I'll use, but we'll see it once we see the algorithm. It'll be clear. I just want to say it's sort of it's not much larger than checking for membership in sets in the collection C. Identifying. So if the sets in the collection C, again, can be identified by size S Boolean circuits, the size of the Boolean circuit implementing the predictor can be just polynomial in the error parameters times S. Okay, and the complexity of learning, so the predictor itself can be simple, but the complexity of learning it can be large. Good. And I should say that the definition of multi-accuracy and multi-calibration is work with Herbert, James, Kim, and Reingold, and there is another work by Kearns et al. That defined kind of these multi-group notions for other fairness measures. So this is the theorem I would like to prove. I would like to show the learning algorithm. Questions about the theorem before I move on? So here I'm talking about when I actually come up, the predictor we can come up with in the end that is multi-accurate. It's sort of compact, it doesn't have large complexity. The predictor itself, the function that maps individuals X to their prediction P tilde of X, that's not so complex. But the learning algorithm, the procedure that runs on labeled data and produces this P tilde, that can require a lot of running time.
Oh, so the predictor can have an easy function, learning that can be hard.
Exactly. Okay, so the learning algorithm is simple. So yeah, we're trying to learn a predictor. So what we'll do is we'll run iteratively. We'll start with a really dumb predictor that just gives probability 1/2 to everyone. And then we'll start trying to improve it. So iteratively, we'll try to see, does there exist a set in our collection? We're sort of looking for evidence that this predictor is bad, or it doesn't make sense. So does there exist a set on which the predictor's expectation is off? If there is, we will correct the predictor on that set and repeat again and again and again and again until for all of the sets, the expectations of the predictions are accurate, and then we terminate. Okay, so simple algorithm. So if there exists a set S in our collection, whose expectation is off by at least alpha. So the expectation over D of P tilde of X, no, I wanted it the other way around. Of Y conditioned on X and S minus the expectation over D of our current P tilde of X conditioned on X and S. If this difference is large, say bigger than alpha, cheating a little bit, then we have to do something, right? Then we're not multi-accurate, we need to correct the predictions. I'm going to call this quantity delta, the difference between the true expectation, the signed difference between the true expectation and the current expectation of P tilde. So if the absolute value of delta is larger than alpha, we need to update our predictions, we need to fix our predictions, so how should we do it? Say again? Add a multiple of delta. Add all of delta. Why settle for a multiple? Okay. So then we'll just update for all of the members of S. We will update their prediction up or down by delta. Okay, so if the expectation of the members of S was 0.1 below, if the predictions were 0.1 below what we see in the labels, we increase everyone's prediction by 0.1. And a tricky point that I will do my best to elegantly avoid, but I think you guys are going to keep me honest, is this might bring the probability below 0 or above 1, right? Like if someone is already at 1 and now we increase them by 0.1, they go to 1.1. We don't know much about probabilities, but we do know that they have to be between, the true probabilities do have to be between 0 and 1. So we project, you know, if for some reason your prediction went above 1, we will project it down back to 1, back to the interval between 0 and 1, okay? Anyway, don't worry about it too much. That's just, it's going to make a technical point. Okay? So we keep doing this, and what happens when there is no such set? We stop, right? We're done. Now there's no set where our expectations are off. So we just halt and we output this P tilde. Okay, so that's a simple enough algorithm. One question is, I said it worked on labeled examples. Where are the labeled examples? Oh, yeah, I'll see the question. So where are the labeled, like where's the algorithm's input? Certainly, you know, it needs some access to the distribution, so where is that happening? Right, so this, in order to know the expectation of Y for the members of S, we need enough examples in order to be able to accurately estimate these expectations for all the sets in S. Okay, so in particular, going back to the uniform convergence argument we saw yesterday, Chernoff bound plus union bound tells us that once we have log of C times 1 over alpha squared, forget 1 over tau or 1 over tau squared, once we have that many samples, we can accurately estimate all of the expectations for all the sets in C. And that's all we need for this algorithm in terms of access to the distribution. Question? So, good. So, did I want to say it? Yeah, so what's the output of this algorithm? What does the P tilde we produce in the end look like? So I promised you it was going to be not much more complicated than identifying sets in C. I'm not fixing a priori a model class, but a property of this algorithm, once we see it, we see what the output is, you know, and it's not so complicated. Okay, so the output of the algorithm is just a list of sets we found along the way, and the nudges, the deltas, by which we increased or decreased the probabilities for the members of the set. Okay, so the output of the algorithm is just some set S1 and the nudge delta 1 that we made for members of that set, and then the set S2 for the second iteration, and the nudge that we made delta 2, all the way up to however many iterations we had, assuming the algorithm stops. You know, maybe it goes on forever. No, so think of it as exponential. An exponential number of circuits.
Don't we have an exponential number of S's in our output?
That's a good question. So maybe we have an infinite number of S's in our outputs. You know, maybe I try to fix one set's probability, one set's expectation, and that ruins, you know, I try to fix set 1, that ruins set 2, and then I go to set 2 and I fix its expectation, and that ruins set 1, and maybe this goes on forever. That's a valid concern, but we'll prove that it doesn't happen forever. So in fact, the number of sets, so let's just agree that if the algorithm halts, then we're very happy, right? The p tilde it produces is multi-accurate. And now our question is, A, will it halt? And B, how many iterations, right? Like how complex at the end of the day is this predictor that we learned? So I just didn't say it, so I'll say it explicitly. At the end, we have this list of sets and nudges, and our prediction for any x that comes along now, the output of p tilde, we just find all the sets that x was in, and we add up all the nudges, starting at 0.5, that was our initial thing, and that's in the end our prediction for x, you know, our prediction for x, projecting along the way if we have to. Okay. So, good. So the question is, what is n, right? Once we stop, we're happy, but will we stop? So the claim, or the theorem, is that the number of iterations we have is going to be just polynomial in 1 over alpha and 1 over tau. Okay, so after a small number of iterations, the algorithm will stop, and our predictor is not so complicated, right? All it's doing is it's taking, essentially if alpha and tau are constant, a constant number of sets, and checking for membership in them, and then adding, you know, the nudges in order to come up with an output probability.
Are these sets defined based on the demographics or just features?
So say again, are the sets defined based on demographics or? Everything, yes, yes, yes. All the answers are yes. So, of course, we want to capture demographics because we want to protect protected groups. But we'll also look at things, you know, if I'm thinking about loans, I am imagining looking at income and education history and employment history and loan history and essentially any combination of features that may be relevant to identifying qualified loan applicants. I'm happy for it to be included in checking for set membership.
And a quick follow-up. So yesterday, I guess Cynthia mentioned the issue with demographics is we don't know which groups we need to look at and how do we even identify all the enumerations?
Yeah, great. So you're saying, you know, how do we even know who the groups are or what groups we should worry about? And here, you know, one nice thing is that we can slightly get away, we can't really get away from that question, but we just include all the groups, right? Like everything that's related to demographics, all the protected groups you might worry about, every combination of demographic attributes that you're worried about, you can include here, a set for them. So in particular, this captures intersectionality, I think, in a nice way. And it lets us get away from needing to worry about defining very precisely exactly what our protected sets are, because we can just have an incredibly rich collection of sets, at least until we start thinking about computational concerns. The collection of sets can be so rich that it includes many, many, many of the things we would worry about.
Does this always happen? So can you have a, I guess, apply this when the, I guess, y's or the things you're trying to estimate are not between 0 and 1? Like if they could fall anywhere on the real line, can you still?
Yeah, so you can apply this type of methodology for richer outcome spaces. So maybe y's are on the real line between 0 and 1. Maybe we're in sort of a multi-class prediction problem where we have 3 colors that are possible and we're trying to predict what the distribution over colors is. So you can apply similar types of reasoning for those problems where you would replace, maybe expectations make sense, but maybe you would also worry about higher moments, maybe you would worry about other concerns. And there are works, so in particular the work about multi-moment calibration, or multi-moment calibration. There's work that really digs into this. Maybe I'll mention it tomorrow when I talk about outcome indistinguishability a little bit.
So I guess a follow-up to that, it feels like the claim that you can do this without hurting accuracy is kind of misleading, because say we're on the real line and we fit some linear regression model. And I'm just using that over logistic regression because that's provably minimizing the mean squared error among that class. Now you've stepped out of that class, so you've post-processed your regression and done some tuning at the end. I don't know if this makes sense. It's just
so there's a couple of things that you're getting ahead of me on, but I want to say, so you're making the suggestion of, first of all, I started with this really dumb initial predictor giving everyone a half, but I could start with something much more intelligent, right? Like I could start with some sophisticated model that was trained to minimize some complicated error and still run this as post-processing. And the claim that I haven't made yet, but I will make, is that this won't hurt accuracy. It won't hurt at least L2 accuracy. Or for any measure of accuracy you want to preserve, you can come up with a post-processing, essentially, that will not hurt it. Now you're right that what I'm doing as post-processing is stepping outside the class, so maybe I'm cheating a little bit. On the other end, I would say I'm, assuming my collection of sets is not too complicated, then I'm not stepping too far out of the class. Okay? And I'm getting what I think is a meaningful guarantee for that little bit of added complexity. Good, so just a word about the complexity. So at the end we produce this short list, so the predictor we have at the end is pretty simple. The complexity of the algorithm, at least as I wrote it down, in every iteration we need to enumerate over all the sets in C and check multi-accuracy on each of them. So if C is exponential, the algorithm, if we do brute force search, is going to be exponential. One hope you could do is you could try to use sophisticated machine learning technology to speed up this search, to not do a brute force search. I won't talk about it. Well, maybe I'll talk about it a little bit tomorrow, about the running time. Good, so the main thing I want to do in the time we have left is to prove this claim to you, that the number of iterations is small. And the way we prove it, or the way you prove such a statement, there's a popular proof technique which is called a potential argument. So you define some potential function. You show that in every iteration, the potential, think of it as like the height of where you are, every update decreases your potential significantly. So if you start with a bounded potential, you can't have too many updates before the potential hits 0, and then essentially you're done. Okay? So we define a potential function for which you can never go below 0, it's bounded in the beginning, and every update decreases it, so we won't have too many updates. Okay. So, let's do that. So, I want to make a simplifying assumption, just to make our lives a little bit easier, that the distribution D is uniform over some subset of, say, capital N elements. I mean, not the whole domain, not all of X, but there's some subset and it's uniform over that subset. It'll just make our lives, it's not a meaningful, you can get away without it, but it'll just make our lives a little bit easier. And then I want to claim that every time there's an update, so we find a set S, I should have said S, that we also assume that the probability of S is at least tau. So every time we find such a set and we update our predictor from p tilde to p tilde prime, the potential goes down. So and the potential function is just going to be the L2 distance between the predictor and the truth, p star. Okay, so we don't know what p star is, but we can reason about it in our argument, and that's going to define our potential function. So the claim is that in every update, when we move from p tilde to p tilde prime, if we look at the distance of p tilde from p star, so the L2 squared distance, and we look at the distance from the updated p tilde prime, let's call it p prime, maybe. It's a little bit clearer. The distance shrinks. Okay, so it shrinks by at least n times tau times delta squared. Okay, and if you look at it carefully in the beginning, the distance can be at most n. Every time it shrinks by n times tau times delta squared, so how many iterations can we have? At most 1 over tau times delta squared before we get to 0 distance. Once we're at 0 distance, we are at p star itself, and p star is multi-accurate. Okay, so we won't actually get to p star, but that's sort of an argument bounding the number of rounds. In the worst case, that certainly bounds your number of rounds. Okay, so why is this true? Well, let's open it up. So what's the square distance, the squared L2 distance between p star and p tilde? That's just the sum over all the individuals in the set S of p star of I minus p tilde at I squared. Right, and let's open up the other expression for p tilde. So similarly, we just have p star of I at I minus p tilde at I. Now, I apologize, but for lack of board space, I'm just going to erase and overwrite what I'm doing. So if you're taking notes, write quickly. Squared, yes, sorry. Okay, so let's just replace p tilde I. We know what that is. In the algorithm, that is just p plus delta. Right, that's the nudge we did for the members of S. Does someone want to scream out and object at this point? I'm only summing over S because everywhere else, nothing has changed. The projection, yeah. So let's ignore it. I'll just say in a word, the projection will only decrease the distance from p tilde, from p star, right? Because p star is always between 0 and 1, so when we project, we're only getting closer to p star. So we are subtracting something smaller or larger, the directions will work out. So we're trying to prove a lower bound, and it works out for us. Okay? Yeah, good. So here we're subtracting something larger. So just have a greater equal sign, and that works out for us. Okay, so now, unfortunately, or fortunately, we have to do a little bit of arithmetic. So the p star I squared is going to appear here and here, and they're going to cancel out for all the members of S. Okay, so let's ignore them. So what do we have? Notes. Yeah, and there's also going to be a p tilde squared that's going to cancel out here and here, so we can ignore those as well. And the remaining term, well, here we're going to have minus 2 times p star I times p tilde I. And here we're going to have plus 2 times p star I times p tilde I plus delta. Right? Minus and minus cancel out. The pi squared is also going to cancel out, and we're going to be left with 2 delta p tilde I plus delta squared. Let me just see, let's see quickly what the signs are. So minus and minus, right? Someone going to keep me honest? Yeah. So here I would have a plus, right? Plus this whole thing squared. And then I have a minus here. I think it's right. Right, I would have here pi squared, everything, there's a minus sign in front of everything. So pi squared minus 2 p star I times p tilde I plus delta. But then we have the minus sign, so that's becoming a plus. And then we would have plus inside, before the minus sign, we would have plus p tilde I plus delta quantity squared. But we have the minus in front of it, so. Okay, so you can check we can check calculations during the break. So my main point in going through this, at this point it's a homework exercise, but I just want to say it's not complicated. Okay, like this, it's not a complicated proof, these types of potential arguments, and it's something nice to know. So just to say what this boils down to, and take it as a homework exercise, and maybe if I'm cheating, tell me that I was cheating and I will be mortified. That'll be fun. So at the end we get we move 2 delta ahead, we get something that looks like 2 delta times the size of the set S. This is just elementary developments minus delta squared. This delta squared is being summed up times the size of S. And this is equal to exactly delta squared times the size of S, which is, we're only looking at sets that are at least of size tau times n, right? The sets have to be large enough, so it's at least delta squared times tau times n, which is what we wanted to prove. So that's our potential drop in every round of the algorithm. Good, and the other point I wanted to make about it is that notice that what we're showing, the improvement we're showing in every update, is not just an improvement in some made-up potential function that we don't care about. It's a really important potential function. It's our distance. It's our L2 distance from P star. So every update, if it happens, is bringing us closer and closer to P star, and this is going back to the question about post-processing. So whatever predictor I start out with, if it's not multi-accurate, and I run it through this post-processing to make it multi-accurate, if the predictor is changing, it's changing in the right direction. Okay, that's an important point. And tomorrow, I'll talk a little bit more about multi-calibration. So multi-calibration, stronger property than multi-accuracy, but there is a similar algorithm for achieving it. You sort of look for violations and you update when they occur. I won't explicitly spell out that algorithm. And we will talk a little bit about the computational complexity and hardness, computational hardness of multi-accurate and multi-calibrated learning. Anything you want to add? No? Okay, perfect. Thank you.